SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. I welcome to this course Advanced Thermodynamics and Combustions. Today we are going to start module 4, that is properties of gas mixture. So in this module there will be 4 lectures that consist of the followings. First one is ideal gas and real gas. Second one is gas mixtures and multi-component systems. Then we will focus towards only for ideal gas mixture, and subsequent in the last lecture we will be discussing about the mixing analysis of thermodynamic systems and in particular for a ideal gas mixture. So in fact till this point of time in all previous modules we have been concentrating only on pure substance, and now we will be concentrating more towards the mixtures and multi-component systems. By this I mean this mixture can be composed of gas or liquid or solid. Mostly when you use the word mixture, it is mainly for gases, and this mixture can also have consist of different gases or different phases, all these things. And the focal point of this module is to how to perform the thermodynamic analysis first thing, and to do this thermodynamic analysis we need to find out the composition of the mixture, number 1. Number 2, for each constituents of the mixtures we also need to calculate the thermodynamic properties, and all previous studies which were used for a pure substance through PVT relations, what we have derived through Maxwell relations and other thermodynamic considerations, that we are going to use it in while analyzing the mixture. So with this viewpoint let me start the first lecture, and in the series it is lecture number 15. The first lecture of the module 4 is ideal gas and real gas. Under this ideal gas and real gas, we will start these considerations with very basic backgrounds through some basic philosophies what we have used for pure substance phases. Then we will move on to state equations, and thermodynamically where we need to represent the state equation for a pure substance and gases. Then we will introduce a compressibility chart, and which is mostly used for gases, and we will see what is this significance, how this is correlated with the equation of state. And followed by this compressibility chart we are going to frame some real gas models, and of course to have more estimate, to have a thermodynamic estimate, we also have to think about ideal gas model. In fact this ideal gas model we have been using in all our basic courses. With this ideal gas estimate we will try to see what benefit we are going to get while analyzing the state equations through a real gas model or through compressibility chart, all these things. So let me start the first topic or first term, which we call this as a pure substance and phase. Now about this pure substance and phase, in the basic thermodynamic course most of the contents have been covered, and in this lecture we will just touch upon some or refresh some of our basic things before you go for the real gas modeling. So, basically the phase refers to the quantity of the matter which is homogeneous throughout in both chemical composition and physical structure. The homogeneity of the physical structure means that the matter is in solid, liquid or gas phase. In fact, that is the three different phase of matter. Now, out of these three phases, two phases of matter can coexist during a change of phase. We all know what is vaporization, where liquid changes its state to gas, melting solid goes to liquid, and sublimation where solid goes to gas phase. Now, for all these phase, when you define a pure substance, it has a uniform invariable chemical compositions, and it can exist in one or more than one phase with same chemical composition. And we all know that the pure substance is represented through PVT diagram, pressure volume temperature diagram. A general rule on state principle determines the number of independent properties required to fix the state of the system. Now, for a simple compressible systems, we require two independent insensitive thermodynamic properties to fix the values for all other insensitive properties, or in other words, there are some measured parameters and there are some derived or calculated parameters. So, the measured parameters are nothing but the independent and insensitive thermodynamic properties, and that is used to calculate all other properties. The three regions of the phase of the substance are represented graphically on a pressure, volume, temperature surface. The single phase region requires two independent properties, while two phase regions are defined through one variable, either it can be a saturated pressure or temperatures. So, this particular diagram shows the PBT surface for a pure substance that contract during freezing and some substance that expands during the freezings. So, all these basic philosophies has been covered in the basic thermodynamic course. I am not going to get into these details, but what I am trying to say is that when you discuss about this PBT surface, and this is a three dimensional structure, now you have to bring down into two dimensional systems, where we represent the characteristics of the substance either through pressure temperature diagram, and normally we call this as a phase diagram, temperature volume diagram or pressure volume diagram. Okay. So, let us start the first diagram, which is called as a phase diagram, where most of the critical informations are framed. Now, if you look at this pressure temperature diagram, and this is nothing but the PBT surface is projected on a pressure temperature plane. What we observe is three different regions: solid, liquid and vapor regions. The solid and vapor region is separated by a curve what we call as sublimation curve. The solid and liquid region is separated by fusion curve, and the vaporization curve separates the liquid and vapor region. And on these PT diagrams, we also define a point we call as a triple point, where all the three states of the matter coexist. Now, when you talk about the critical point, at that point liquid and vapor they coexist, and same philosophy, solid goes to liquid or liquid goes to solid, melting or freezing, liquid goes to vapor or vapor comes to liquid, we call vaporization or condensation. Now, here we use the word mostly solid goes to gas, so we call this as a sublimation. Okay. Now, on this diagram we have fixed the point what we call a triple point and the critical point. To summarize these things, what we can write is that the two phase regions are reduced to lines, so either sublimation, fusion or vaporization curve, and any point on this line represents the phase of the mixture at that temperature and pressure. Now, state at which the phase change begins or ends is called as a saturation state. The saturation temperature normally designates the temperature at which the change of the phase takes place, at a given pressure, and we call this as a saturation pressure. Thus, every saturation pressure has a unique temperature and vice versa. And on this phase diagram, we also define the critical point, which is the melting location of saturated liquid and vapor, and the critical temperature Tc is defined, which is the maximum temperature at which liquid and vapor can exist in equilibrium corresponding to state Pc and Vc. And the triple line on a 3-dimensional PBT surface reduces to a triple point in a phase diagram. And this triple point for the water is located at 0.6113 kilopascal and 273.16 Kelvin. The line that represents the two-phase solid liquid region on the phase diagrams slopes left for the substance that expands during the freezing and to the right for the substance that contract during the freezing. This is the characteristics of the phase diagram. Then move on to pressure volume diagram. We all know pressure volume diagram. We have a pressure volume diagram for substance that expand during freezing and that contract during freezing. So, the pressure volume diagram is important because it distinguishes the liquid vapor state or vapor liquid state, and normally it is recognized through a dome. Now, within this dome, the state of the system is liquid plus vapor mixture, and outside the dome it is either liquid or vapor. In a single phase region, if this temperature is greater than critical temperature, then the pressure decreases continuously when the specific volume increases, and the critical isotherm passes through the point of inflection at the critical point and slope is 0. This is the characteristics of pressure volume diagram. So, in the similar line, we also frame temperature volume diagram when PBT surface is projected on temperature volume plane. Here also we define this critical point, critical pressure, critical temperature. Same logic applies here in a single phase region. When pressure is higher than the critical pressure, the temperature increases continuously when the specific volume increases. The critical isotherm also passes through the point of inflection, that is at this point, and the slope is 0. Now, having said this, we will now move on to the equation of state. Now, all these things data which we have shown here, that was the mostly for water. I mean, in fact, in our study we mostly focused on the properties of the pure substance, mainly concentrated for water. But if there are many more substances and each substance must have the PBT data, but it is also not possible to generate the data for all the substances similar to steam table, but we have some data for refrigerant tables, and we also have some data for some important gases. But the main issue is that always it is not possible to have a block of bulk data which are normally used to specify the state of the systems. So, the PBT relations for the pure substance, people have considered different methods. First one is mathematical representation of thermodynamic properties. That means, you get the set of data, limited data, and use the thermodynamic property relations that we have discussed in our earlier module, where properties like internal energy, enthalpy and entropy, they are represented with respect to measured data, that is pressure, temperature and specific volume. And tabular representation of the properties, that means we have seen, or it is known that we have steam tables, we have refrigerant tables, where the property relations are available in the form of data sheets. Then other way of representation of PBT surface is through Mollier diagrams. We all know that enthalpy entropy diagram is called as a Mollier diagrams, and this is normally used when you are using Rankine cycle or steam power systems. Then we have other type of charts, data, PB surface data represented in terms of compressibility chart, which we are going to discuss today. In addition to that, we have some formulations, mathematical formulations involving state equations, and in fact these equations in general are applicable to most of the substances. However, their relative accuracy may change, and we, while doing this analytical formulations, here our model comes, what we call them as a real gas model. So, in a special case, the thermodynamic property evaluation in gas phase, and this is normally considered as state equations for ideal gas or real gas models. But these gas models are also applicable for mixing systems, multi-component systems. Of course, we are thinking them only in single phase, and that is gas phase. And we are not going to go for any complicated multi-component systems, and in our focal analysis we will be talking about mixtures, we will be talking about the data when there is a combustion takes place or during a chemical reactions. Only these two things we are going to focus in this course. So, let us give the introduction that what is the equation of state, how it has framed from the beginning. Now, when we talk about the equation of state, we normally refer to a pure substance when it is in gaseous phase. Now, a gas is, why you say it is a gaseous phase, and in this gas phase we have some best behaved thermodynamic considerations. So, a gas is considered as to be a well behaved thermodynamic substance, that is because the ratio of pressure of the gas P to the triple point pressure approaches to a value which is independent on the nature of the gas. When P or triple point pressure approaches to 0, that means when you go to 0 pressure, all of them behave in a similar manner. And there then the limiting value of this ratio, when it is multiplied by 273.16, defines the temperature at that pressure, and normally we call this as a ideal gas temperatures. This ideal gas temperature word we have been using most frequently starting from the second law of thermodynamics, and of course to some extent third law of thermodynamics, when the temperature reaches to absolute 0. So, under those circumstances an interesting phenomena happens, and it has been an experimental evidence that when P tends to 0, the product of PV approaches to same value for all gases at that same temperatures. So, functionally we can write limit P V bar, and here V bar is nothing but, and in most important thing here we will be talking about molar analysis. So, where V bar is nothing but your molar specific volume, that is V by N, N stands for number of moles. And when you do this molar analysis, so instead of R, which is characteristics gas constant, we should be using universal gas constant R bar, and its value is 8.3144 joule per mole Kelvin. Okay. Now, to have these understandings, so at constant volume this T can be written as 273.16, and when this limiting value P Tp goes to 0, P by Tp. Now, after simplifying this, we can get an important relations, limit P V bar or is R bar T. Limiting value of P times V bar goes to R bar times T, or in other words limit P capital V goes to N times R bar T. This relation is very vital for the all the subsequent analysis for the consideration of equation of state. Then moving further, the relation between PV and P, that is pressure multiplied volume, and P, if they are taken as independent entity, they are often expressed for real gas by means of power series expansions. Now, before the equation of state is framed, people used to represent this PV bar is equal to as a power series expansion, which is A times 1 plus Bp plus Cp square plus dpq and so on, where A, B, C, D they are considered as a virial coefficients. This is how the mathematical way of representing the equation of state. Then after considering this experimental evidence, then the revised form of the equations in the form of virial coefficients is represented as P V bar by R bar T is equal to 1 plus Bp plus Cp square plus dpq. So, what people have said that when from these equations it was said when PV bar by R bar T is equal to 1, it was said it to be ideal gas, means all ideal gas model will be followed like this, and for all other situations, now when it is a function of pressure, then it becomes a real gas model. So, that means PV bar by R bar T becomes 1 plus if any other value is there like Bp plus C P square. So, all these things when it comes, it becomes a real gas model. So, this was the time when the state equations were defined through this concept of virial coefficients. Here if you look at this equation, pressure this particular parameter PV bar by R bar T was considered as a function of pressures. The other equations they consider like one Bretty-Bridgman equations, they consider instead of P they represent these state equations in the form of T and V, where both T and V bar becomes the parameter in the right hand side, and accordingly the virial coefficients were determined. So, it all depends whether we consider it as a pressure explicit equations or not. Then moving further, so when you deal with these state equations, there are lot of mathematically complicacy while analyzing the data. So, what the concept that has been developed and we are going to study now is the compressibility charts. Let us represent all the data in a graphical manner. So, what this graph shows is that, and of course, this compressibility chart is defined as all experimental evidence for all the gases. What has been to start with, what was done is that we take two parameters, one is P V bar by T, and here V bar is your molar specific volume, and another parameter was considered as a P. Now, for a given gas at temperature T1, we can find out these values, we can plot these values at T1 set of data, we can plot it. That means, we find P corresponding this number PV bar by T at a given T1, we can get the first graph, and the second graph also was taken at temperature T2, the third one T3 and T4, and this is done for a particular gas. What interesting point is that now based on the data which are available to us, okay, when they are plotted during the after experiment, we get a set of data, maybe I can say this domain of the data which are available to us is in this dome. Now, if by plotting them and you extrapolate it further, I mean if you keep on extending data or extrapolate it, interesting fact is that it intersects the y axis, that is PV bar by T axis at one point, and normally what we call this R bar, that means, or you can say limiting values of PV bar by T is nothing but your R bar. So, this is what the significance of the universal gas constant. So, people have said is that this is nothing but your universal gas constant. Then it was realized whether it is true for all the gases or not. So, that means similar plots also can be generated for different gases. So, it happens in the situation that there are a lot of gases, there are a lot of pure substance, many gases are there. So, in such cases, instead of putting this particular graph for different gases, people have used the concept of non-dimensionalizing is. So, what with this philosophy we represent this graphical concept as compressibility chart. So, the understanding of relationship among pressure, temperature and specific volume of the gas is represented through a parameter. First one is the compressibility factor, which we are going to introduce Z as PV bar by R bar T or PV by RT, where R stands for R bar by M and R is your gas constant, R bar is your universal gas constant, which is nothing but this particular graphical number when PV bar by limiting value of PV bar by T. So, this universal gas constant has a unique value for all gases and it is defined as the limiting value of PV by T when the pressure changes to 0. Dimensional ratio, which is known as compressibility factor, and at states where gas pressure at states of gas where the pressure is small relative to the critical pressure, the Z value is close to 1. That means, if Z is equal to 1, it is like we can say PV bar is equal to R bar T, but in many situations it is not so sure, not true, and we call them is that it is a real gas model. So, entire idea to represent this graphical method into a non-dimensional form is the concept of principle of corresponding states. So, what I can say that if I plot Z versus pressure which was shown graphically, it is true for one particular gases, but when you do this we call it as a compressibility chart for that particular gas. Now, we are going to frame a generalized compressibility chart and which is true for all the gases. Now, to do that a non-dimensional parameters were introduced and we call this as a reduced value. For example, we introduce the terms critical pressure, critical temperature, critical pressure Pc, critical temperature Tc and critical volume V bar by C, molar specific volume. Now, for each gas these numbers are unique and the actual pressure value P, when it is divided by to this their critical numbers, it becomes a non-dimensional number which is called as a reduced pressure. So, in our previous analysis when this plot was done, when you have pressure P and Z which is nothing but PV bar by RT. So, if you see this was unitless, no unit, and this has some unit, pressure means it is either bar or Newton per meter square, and these data were taken for a given gas. So, this concept was changed with respect to this particular figure where this P is replaced with a reduced pressure PR, and this reduced pressure we get for a particular gas Pc by normalizing it with respect to its critical pressure, and y axis remains what we say Z. So, likewise for different gases one can have a set of data involving, and that data we can get it for different temperature ratios. So, that means if you look at one particular temperature, let us say TR of 1.2, then on this TR of 1.2 we have data for methane, ethylene, ethane, propane, all nitrogen, oxygen, all sorts of things. So, all this particular curve talks about only for TR is equal to 1.2 and it is true for all these gases. So, this behavior of all the gases was considered as a advantage, and that is the reason we call as a well behaved. They are well behaved at reduced values. And here another term I need to emphasize here, that pseudo reduced specific volume. Normally the idea is that when you see this data, the data are represented in the form of PR and TR, but to calculate this corresponding VR, because PR and TR they are calculated based on the critical value of this substance, but VR was calculated based on the molar specific volume which is already there and its critical pressure and temperature, that means from critical pressure and temperature data. So, that is what a different name was assigned, what is called as pseudo reduced specific volume. Okay, by doing things, a realistic model what we call as a compressibility chart is available in these many books, and I have taken the extract from this book Moran and Shapiro, which talks about this compressibility chart in which the reduced pressure and Z was plotted at different TR, and of course in different PR regime. Like this particular figure talks about PR less than 1, this particular figure talks about PR less than 10, and any things which is less than 40, between 10 and 40, it is plotted in this manner. So basically speaking, that having knowing the value of PR TR, one can directly refer this compressibility chart to find Z, or knowing Z and PR we can find TR. So likewise, and this is true for all the gases, and this concept we call this as a compressibility chart. Now moving further, we are now going to discuss some of the real gas model. So till this point of time, the representation was done in a graphical manner and through a compressibility chart, but here many times people are comfortable in writing in the form of equations, and we call this as a real gas models. And out of these two real gas models, there are two important workable models, means widely used models, and they involve two constant equations. Like in a real equation state, there are multiple number of constants A, B, C, D, like this, but most widely used are two constant equation model. One is Van der Waals gas equation, other is Redlich-Kwong equations. So we will emphasize only these two gas equations. Now the first one is the Van der Waals gas model, and in fact we all have aware of this model, that when this model was introduced as a real gas model, it was necessary justification was made that the gas molecules occupy more volume with respect to ideal gas model, where now in the ideal gas model the size of the molecules were neglected, but in the Van der Waals gas model the size of the molecules were taken into account. So as a result, the effective volume is reduced. But what happens, due to attractive forces between the molecules, they exert lesser force in comparison with respect to ideal gas. Means the gas molecules exert less force on the container because they have on the container of the gas, or maybe the walls of the surface in which they are contained, because the force of attraction between the gas molecules. So a mathematical form of Van der Waals equation involves, by considering these two effects, is P is equal to R bar T divided by V bar minus B minus A by V bar square. So here if you look at these equations, the parameter B takes care about the finite volume occupied by the molecules, and the parameter A by V square talks about the pressure value which was supposed to be for ideal gas, which is higher, gets reduced by an amount by A by V bar square. And here also the constants that are appearing in this equation, that is A and B, must be found out from the PBT data. Now how do you find out the data for a real gas model, and in particular for a Van der Waals equations? So a set of single constants, that means how do you find out this value of A, B, C, and then we are going to put them. So to do that, one way to look at is that we write this equation, that is Van der Waals equation, at the critical point, replacing PC, V bar C and TC. Now at the critical point, important phenomena that happens, that is dP dou P by dou V bar at constant T is equal to 0, and the second derivative, that is dou square P by dou V bar square at constant T is also 0. So differentiation of these two equations will give you two equations, and in fact we are available with also two constants. So at critical point, the differentiation of these two equations will give you the constant values A as 27 by 64 R bar TC square by PC, B is equal to R bar TC divided by 8 PC, and VC is equal to 3 by 8 R bar TC by PC, and ZC, that means compressibility factor at the critical point, is found to be 0.375. So this is the consequence that we get from this Van der Waals gas equations to get this constant term. Now, putting these equations, one can also find out the compressibility factor equations, which is in the cubical form ZQ, Z square, Z, and they are represented in terms of PR and TR. Okay. So, this is how the van der Waals equations is modeled, which is considered as a real gas model. And in fact, when you compare it with your actual model or behavior, it sees that van der Waals equation is the simplest model that accounts the departure of an ideal gas behavior for an actual gas. And the other model, which is the most recent model, and that is in the 1949. So, it is a real gas two constant equations, and it is known as Redlich-Kwong equation. And this equation is explicit in pressure, not in the specific volume. And in fact, the van der Waals, while framing this van der Waals equations, necessary justification was done in terms of volume, in terms of force. But what has been done is that in this Redlich-Kwong equation, it is a empirical in nature, okay, and the equations were done such that, and there is no necessary justification could have been made why these numbers were taken into account. But however, it has been proven that it is better or accurate than the van der Waals equations, particularly at high pressures. That means, at high pressures, the inaccuracy of van der Waals equations becomes significant. So, during that point of time, Redlich-Kwong equation was used, and this particular equation is what we call as P is equal to R bar T divided by V minus B. This is the same term which was appearing in the van der Waals equations, but the A by V square term in the van der Waals equations is replaced with A by V bar into V bar plus B into T to the power half. And with these things, other compressibility factor equations were derived. So, we are not going to get into these details. Here I have just written these values. Of course, these are not the matter of interest for us, rather we are only concentrating only these equations. Now, apart from giving all these explanations for compressibility chart, real gas model, PVT surface, the one best thing that remains is that we have to use this ideal gas model. And this ideal gas model is the benchmark or reference level. Now, if why I should go for real gas model? If an ideal gas model can predict accurately or without going into mathematical complications, it is better that we should go for the ideal gas model. Until this point of time, we have been following this ideal gas model, and just to summarize, in fact, we all are used to this ideal gas model. Just to summarize, when you use this ideal gas model, we first thing we say PV by RT is equal to 1, or in other words, we say the compressibility factor is 1. And here while using these equations, we consider molar specific volume V is equal to V bar by M, where we say P capital V is equal to M RT. Other way of looking at is that instead of specific volume, we use the molar specific volume, where we are introducing the molecular weight of the substance. Then based on this molar specific volume, we can write PV bar is equal to R bar T. And of course, molar specific volume is defined by V bar is equal to V by N. So, PV is equal to nRT. So, one equation is PV is equal to mRT, other equation is PV is equal to nRT. Okay. And apart from this, we also say that for an ideal gas, the internal energy is a function of temperature only. In fact, we have already proved this through our thermodynamic relations. Enthalpy is also function of temperature, because enthalpy consists of U plus PV. Already U is a function of temperature, but PV is also function of RT. PV is equal to RT for an ideal gas. So, because of this reason, enthalpy is also function of temperature only. And one other point that I need to emphasize, that general compressibility stat at states pressure P relative to the critical pressure or lower pressure and temperature T allows us that the compressibility factor becomes close to 1, and we call this as a ideal gas equation of state. So, with this I come to the end of this particular lecture. Now we will try to solve some one or two important problems based on our understanding about this lecture. The first problem talks about the rigid tank contains water vapor, and this water vapor is cooled until the temperature reaches to 400 degrees centigrades. The initial state of water is given as 20 megapascal and 520 degrees centigrades. So, we need to find out calculate the specific volume at its initial state and the pressure at the final state. So, as you see in this figure, it is very easy that one can use this steam table data to find the thermodynamic states, and in fact we all know we are used to it. So, here we are trying to emphasize that how this particular problem we are going to solve by using the concept of compressibility chart, or by knowing the critical point or critical temperature and pressure of water vapor. So, to start with, what data was been given as we have this initial state. So, in this initial state which is we say 20 megapascal and 520 degree centigrades. Final state is 400 degree centigrade, and this final state, since it is a closed rigid tank, there is no change in the volume. So, it is a constant volume process. So, from the steam table, for this initial state we can refer superheated region, and at that superheated region we can find its specific volume V1 as 0.0155 meter cube per kg. Now, at same constant volume, that is at temperature 400 degree centigrade and V1 as 0.0155 meter cube per kg, this it will also give the final pressure P2 as 15 megapascal. So, this steam table data is based on the steam table data, but our job is not with respect to using steam table, rather you have to use the concept of critical parameters. So, by critical parameters means for water, if you refer any thermodynamic data book, we can find the critical pressure Pc for water is 22.09 megapascal. Critical temperature Tc is equal to 647.3 Kelvin. Okay. Now, we have to find the reduced parameter. Okay, reduced parameter I mean for state 1 I can write it as PR1 is equal to P1 by Pc, and this number P1 is 20 megapascal. So, P1 by Pc becomes 0.91, then PR1 T1 by Tc, T1 is 520 Kelvin, that is 793 Kelvin, 520 degree centigrade 793 Kelvin. So, TR1 by Tc is 1.23. So, we have state coordinates PR1, TR1 data. So, this we have to apply it for compressibility chart, that is generalized compressibility chart, and this will give you the value Z is equal to 0.83, and Z we also know that is nothing but P1 V1 by R T1 is equal to 0.83. and we know that R is equal to R bar by M. R is 8314 joule per mole Kelvin and molecular weight for water it is 18. Okay. So, we know R. So, from this data we have P1 20 megapascal, T1 520 degree centigrades. So, this will give you V1 as 0.83 into 8314 by 18 into 793 divided by 20 into 10 to the power 6, and that number is 0.152 meter cube per kg, whereas our steam table data was 0.015 meter cube per kg. So, this was done for PR1 and TR1. Now, for state 2 we can follow the similar process, but here the process was a constant volume process. So, you do not have data for pressures. So, you have to rely on the reduced volume parameter VR2, which is nothing but V2 PC by RTC, and sorry, this is 0.0152. So, 0.0152 into PC 22.09 into 10 to the power 6 divided by 8314 by 18, TC is 647.3. So, VR2 would be 1.12. So, VR2 is this, and TR2 we can find as T2 by TC, that is equal to 673 divided by 647.3, that is equal to 1.04, and with this BR and TR data this will imply PR is equal to 0.69 from the compressibility chart. So, since we know PR 2, then P2 will be equal to, P2 can be calculated and its value is 15.24 megapascal. So, state 2 was 15.24 megapascal, but the steam table data was given as 15 megapascals. So, of course, there is a relative accuracy while considering these two models. And then next problem that we are going to solve about the consistency of equation of states. What we have data is that we have a cylindrical tank whose dimension is given 0.2 meter diameter and 1 meter length. It consists of 4 kg of carbon monoxide at minus 50 degree centigrades. Now, we need to find out the pressure exerted by the gas models. We also know that there are many methods are available. We can use it in the compressibility chart, we can use van der Waals equations, we can use ideal gas equation, we can use Redlich state equations. Now, let us see that in each of these methods what is the accuracy level or what is the value that we are going to get. So, the data that is given is V is pi by 4 d square into L, that is volume occupied by this gas. And that V we can calculate as pi by 4 into 0.2 square into 1, and this number is 0.0314 meter cube. Now, we have this gas which is given as CO, carbon monoxide. So, for which we have this molecular weight 28 kg per kilomole, and this mass is given as 4 kg. And we also need to know R bar. R bar is nothing but 8.314 kilojoule per kilomole Kelvin. So, this data will be requiring. So, first thing data we have to use compressibility chart. So, to do that we need to find Z, and to do that we require PC, and that PC value from the data table for CO is noted as 35 bar. PC is equal to 133 Kelvin. Then we can find out value of PCTC, we can find out TR, that is T by TC. Your T is minus 50 degree centigrade, that is minus 50 means 223 Kelvin. So, TR is found to be 223 divided by 133, this turns out to be 1.68. Then we can find out VR, which is V bar by TR divided by R bar into TC, VR into V bar into PC. So, reduced volume V bar we can find out as M into V, that is equal to M into V by M. That V bar turns out to be 0.22 meter cube per kilomole. By inserting these values we can get VR as 0.7. So, we have this TR and VR information. Using this compressibility chart will give you Z is equal to 0.9. Now, when I say Z is equal to 0.9, we can write this as P into V bar by R bar T, and this will give you the value of pressure. We know Z 0.9, we do not know P, V bar is known as 0.22, R bar is this, temperature is available to is minus 50. So, this will give you P as 76 bar. Okay. This is how we get from this compressibility chart. Then we will go to van der Waals equations, case B. So, van der Waals model equation we write as R bar T into V minus B bar minus B minus A by B bar square. Now, here A is equal to 1.474, B is equal to 0.0395. So, these two we have to find from the data from the thermodynamic book for CO, and V bar is already calculated as 0.22 meter cube per kilomole. So, we all know this number, and then by inserting this value we can calculate P is equal to 72 bar. So, the van der Waals model gives us pressure to be 72 bar. Third one is Redlich-Kwong equations, that takes is that P is equal to R bar T divided by V bar minus B. Here A becomes V bar is reduced as V bar into V bar plus B into T to the power half, and we all know all the value. You have V bar is this, T is equal to 223 Kelvin, and this constants for this case or Redlich-Kwong equation is A is equal to 17.22, B is equal to 0.02737. Now, by inserting this value we can get P is equal to 75 bar. And last one, which is what we call as a simplest one, ideal gas. and if nothing is given, then we must use this gas equations we have been using so far, that is P is equal to R bar T divided by V bar, and all these numbers are given. So, we can find out P is equal to, here I write 8314 into 223 divided by 0.22 into 10 to the power 5, this becomes bar. So, this will give you P is equal to 84 bar. So, as it is clear that ideal gas model always gives the higher pressures, and closer to ideal gas model is your Redlich-Kwong model, and a real gas model through van der Waals equation gives us 72 bar, and of course compressibility chart data gives 76 bar, which is closer to van der Waals equations. Okay, this is how we can say the relative accuracy of predictions while using the real gas concepts. So, with this I conclude this lecture for today. Thank you for your attention.